road here. So we're going to start chapter 4 here. Chapter 4 can be kind of tricky. This is maybe one of the harder things we do in first semester. Last chapter, to be honest with you, if like fractions were less of a problem, is usually one of the easier things that you do in first semester, my opinion. All right. So in chapter 4, we're going to be talking about the inverse trig functions and kind of how to use them. Before we start talking about specifically inverse trig functions, let's talk about inverse functions again, right? We did this in chapter 1, right? What do you guys remember about how inverse functions work? Great, so that's something there. Yeah, so like more generally, but we'll get to that idea because that's a good one. So say we have some domain and some range. Our function then takes something in the domain and sends it to something in the range, right? Like, for example, it might say f of 3 and it sends it to 5. Right? F inverse then is going to take that thing in the range and send it back to the domain. So for example, if we take the same 3 and 5, F inverse is going to take 5 and send it back to 3. Right? That's basically what our inverse is doing, is just undoing whatever F did. Cool. So if F is a set of xy's, F inverse is the set of yx's. Yeah. Everybody's okay with that? So now let's think about trig functions here specifically. And let's just start with, yes, sir. Those are reciprocals, but not necessarily inverses. Okay. Let's start with the trig function, though. Let's just say we start with sine x. Right? So if I think about the graph of sine x, it looks like this blue right here, right? Graph of sine x. So this graph is made up by a whole bunch of xy's, right? If I swap the x and y coordinates for every point on that curve, I get this blue curve. Or this light blue curve, or teal, or whatever color. Let's just make it a more obvious. This red curve. Everybody's okay? So all I did was swap the x and y's from the blue to make the red. What do you notice about this red curve? What problem do we have with it? What's that? It's not a function. Excellent. How did you know it wasn't a function? Just by looking at it. It fails the vertical line test. Yeah, right? So that's a problem for us, because what that means is if I plug in some value of x, I'm going to get, like how many y's? If I say I plugged in x equals 0, how many y's would that give me for the red curve? Three that you can see right now, but does this thing keep going?
Yes.
How long does it keep going? Forever. And does it keep doing the same thing over and over and over again?
Yeah.
So how many outputs am I going to get? Infinitely many. Oh, that's a nightmare. So we don't want this to be our sine inverse because we don't want to be worrying about infinitely many outputs, right? That stinks. Nobody wants to deal with that. So what we're going to do instead is we're going to go back to sine x. And instead of taking all of sine x, we're just going to take part of sine x. So the part that we want is the smallest part of sine x that still covers the entire range of sine x. So maybe we'll start here and go to there, right? That covers all of our y coordinates that we'll ever use for sine x, but that's the shortest section of it that will do that. Everybody's okay? So let's update our graph by doing that. So now I have just this little piece of sine x. Everybody's okay? And if I then swap the x and y coordinates for that, I get this purple graph. Is that a function? Yeah, right? That passes the vertical line test. No issues there. That's what we're going to use for sine inverse because now it's a function. We're only going to get one output. Everybody happy? So let's summarize what we just kind of did graphically, right? We took sine x, who had a domain of all real numbers and a range from -1 to 1. We restricted its domain from -infinity to +infinity to -π/2 to +π/2. The reason we did that is that's the shortest domain whose range is still going to be -1 to 1. Thanks, boss. Everybody's okay there? And so now, let's, instead of calling this y equals, I'm going to change this to f of x. It'll make the notation I'm going to use here just a little bit more clear. So if I then take a look at f inverse, we'll call that function sine inverse of x. Now to make f inverse, what do we do with our coordinates? With the x's and y's? We switch them, right? So remind me again, what coordinate is the domain talking about? X. So the domain in f of x is going to become what for sine, or for f inverse of x? It'll turn into the range, right? Because the x and y's are flipping. And then the range for f will become the domain for f inverse. So far, so good? So this is kind of how we're defining sine inverse. So far, so good? Okay. So let's look at an example of using this function now. So let's say we're asked to find the exact value without a calculator for sine inverse of 1/2. If we're asking you to do anything with sine, cosine, tangent, and not asking you to use a calculator, what are we going to be using? Sine, cosine, tangent, but no calculator. What are we going to have to use? Unit circle, right? Yeah. Do you still have your unit circle I gave you? If you do, pull it out. If you don't, I'll pass some extras along. If you need one, take one. If not, just keep it moving. And I'm just going to kind of pause here for a minute and let these unit circles kind of make their way around if anybody needs one. Okay. Lexi, if you're the last person that's gotten theirs, can you just put them back on top of the file cabinet for me? That stack. Thanks, dude. Okay. Did you guys need one in the back? No, you're good? Okay. All right, so let's take a look at what we have here and how to do this. So the first thing we should do is we should make sure that what we're trying to do sine inverse of is in the domain of the function, right? So is 1/2 in between -1 and +1? Well, yeah, right? It's bigger than -1 because it's a positive number, and it's less than +1, right? Because it's a half. Everybody agree? So we can certainly do this problem. Everybody's happy? What would we say if that was like sine inverse of 7? If it's not in the domain, we're going to say that it equals undefined, right? If you tried to do sine inverse of 7 in your calculator, you're going to get a domain error, which is telling you that, like, hey, you're plugging something in that we can't do. Everybody's cool? So far, so good? Now, I know when I take sine inverse of something, I should be getting a number between -π/2 and +π/2. So let's try to figure out where on the unit circle is -π/2 to +π/2. So I'm going to think about it as two separate pieces. I'm going to think about the chunk from -π/2 to 0, and then from 0 to π/2. So remind us again here, π/2 and -π/2, these are just angle measures, right? What is π/2 the same as in degrees? What angle is that the same as in degrees? 90. Very good. How did you get that? You looked at the unit circle. What do you remember the conversion factor to go from radians to degrees? We multiply by 180 over pi. But yes, this is the same thing as like -90, and this is like the same thing as +90. So if I go and I look at my unit circle, if I start at 0, if I want positive angles, let's go 0 to 90 first. Which way do I go? Clockwise or counterclockwise? Counterclockwise, so starting at 0, if I go up to 90, I go here, right? That's covering quadrant 1. Everybody agree? And if I start at 0 and I try to go to -90, which way am I going to go? clockwise, so I go down to negative 90, which would live right there. So that's all of quadrant 4. So whatever the output is going to come from quadrant 4 or quadrant 1. Everybody's okay with that? Now, when I look at my unit circle, we have all these points on it, right? These x, y's. Does anybody remember what x and y represent on the unit circle? We did this all back in chapter 2. X is not sine, it's cosine. Right? So all the points on my unit circle are cosines, comma, sines. If you have your unit circle with you and want to write that down as a reminder to yourself, go ahead and do that. Probably not a bad idea. Wade, you came in late. If you didn't have your own unit circle copy, there's some, okay. Yep. Okay. So what are we going to do now? We're going to take 1/2 and we're going to look for at the y coordinates in quadrants 1 and 4. So the only place that I see in quadrants 1 and 4 where the y coordinate is 1/2 is right there. The angle measure there is pi over 6. So this should equal pi over 6. I'd need to still check one thing though. I need to make sure that that is in the domain, or the range for sine inverse. So clearly pi over 6 is bigger than negative pi over 2, right? Because it's a positive number. And I definitely know that 1/6 is smaller than 1/2, right? Everybody agree with that? So pi over 6 is definitely between negative pi over 2 and positive pi over 2, correct? So that's my answer. Did we feel okay doing this? So far, so good? Let's do another. So let's say we're looking at sine inverse of negative square root 2 over 2. So first thing I want to do is I want to check to see if negative root 2 over 2 is in the domain of my function. Is negative root 2 over 2 between negative 1 and positive 1? Can you tell by looking at it? Probably not. What could you do to tell? Well, come on, people. You just type it into your calculator and see what the decimal is, right? So negative root 2 over 2 is negative 0.707. Is that between negative 1 and positive 1? Yeah, it is, right? Negative 1 is less than negative 0.707. And that's definitely less than positive 1. So we're good. So what I'm going to do now is I'm going to look in quadrants 1 and 4. I'm going to look at the y coordinates, and I'm going to look for negative root 2 over 2. That's the only spot in quadrants 1 and 4 where the y coordinate is negative root 2 over 2. That tells me my answer should be 7 pi over 4. But I'm not done, right? I need to check to see if that's between negative pi over 2 and positive pi over 2. And what do you see? 7 pi over 4 is 1.75 pi. Correct? That's too big. That's way bigger than pi over 2. Oh no! So this can't possibly be our answer because it's not in the range of our function. However, is there another angle whose terminal side is in the same location of 7 pi over 4 that could be between negative pi over 2 and positive pi over 2? That's a possibility. Do you remember how to find such an angle, or what such an angle would be called? What? Okay, so you're real close. So the type of angle we're talking about are coterminal angles, angles that share a terminal side but are different sized angles. You can find angles that are coterminal by adding or subtracting 360, or if you're in radians like we are, 2 pi. So 7 pi over 4 we said was too big to be on our interval. So should we add 2 pi or subtract 2 pi? Subtract, because we need this angle to be smaller, but still in the same location. So if I subtract 2 pi from this, what am I going to need to have to subtract these two numbers? Common denominators. What would the common denominator be between 7 pi over 4 and 2 pi? 4. So I'll multiply this fraction by 4 over 4. So what's 7 pi minus 8 pi? Negative 1 pi, and then the denominator will still be 4. And we notice that that is definitely between negative a half and positive a half, because negative a quarter is bigger than negative a half, right? Everybody's cool? So helpful hint. Whenever we're doing sine inverse and our answer lives in the fourth quadrant, we'll have to do this same trick. We'll have to subtract 2 pi from it. So anytime your answer, when you're doing a sine inverse, lives in the fourth quadrant, we're going to have to add 2 pi to that answer, or I'm sorry, subtract 2 pi from that answer to get our final. Is that okay? Okay. All right. Now, so far, when we've talked about trig functions, how many trig functions have we talked about? You've lost count. It's not that high of a count. 6 is correct. Sine, cosine, tangent, cosecant, secant, cotangent. That's our 6. We've done sine inverse, right? Let's talk about cosine inverse and tangent inverse. So for cosine, to make this work, we're going to restrict the domain to 0 to 2 pi, or 0 to pi. But our range is still going to be negative 1 to 1. Its inverse function then, cosine inverse, its domain is going to be negative 1 to 1. But its range now is going to be 0 to pi. What quadrants are is handled by, or is covers the angles from 0 to pi? What quadrants? 1 and 2. Good. Now let's do tangent. So for tangent, the domain that we restrict down to is negative pi over 2 to positive pi over 2. But notice this time we are... Hi.
Can I still quiet for a second?
Sure. No problem. But this time we have parentheses on the negative pi over 2 to positive pi over 2. What's the difference between the parenthesis and the bracket again when we write these intervals? The bracket includes the number at the end, and the parenthesis does not, right? Why did we use a parenthesis on tangent instead of a bracket? Well, let's think about what the graph of tangent looks like. What does the graph of tangent have that sine and cosine doesn't? Asymptotes. Yeah, exactly right. Guess what the location of those asymptotes are? They're at negative pi over 2 and positive pi over 2. So those were undefined values. Those were not in the domain of just regular tangent. So if we restrict the domain, I can't restrict the domain to include something that the function before didn't include anyways. That's why there's a parenthesis on the pi over 2 and negative pi over 2 rather than the brackets. Oh, that was weird. So far, so good? All right, let's do a couple more examples. So we're still using the same directions as the previous examples here. Let's do that. Okay. So let's go ahead and find cosine inverse of negative root 3 over 2. First thing I want to do, does that lie in the domain of cosine inverse? Is that between negative 1 and positive 1? Can you tell by looking at it? If you can't, what should you do? Plug it in your calculator and get the decimal, right? Negative 0.866. Does that work? Yep, that's okay. When we look for cosine inverse, what quadrants are we looking in? We're looking in quadrants 1 and 2, right? Okay. Now, what coordinate are we looking for if we're looking for cosine inverse? X coordinate. So I'm looking for the, yes, the X coordinate that is equal to the negative square root 3 over 2. Where do we see that? Right there. So our answer should be 5 pi over 6. Now we need to check to make sure that's in the range of cosine inverse. Make sure that's an acceptable output. Is 5 pi over 6 in between 0 and 1 pi? Yeah, for sure, right? 5 over 6 is definitely bigger than 0 and is definitely less than 1. So we're good. So that must be it. We're done. Everybody's good with that? Now, tangent. How is tangent related to the x and y coordinates on the unit circle? Remember that cosine is x and sine is y. But what is tangent? Ooh, so close. Y over x. So, if we think about this, we're going to say y over x has to equal -1, right? Or if I cross multiply, y and x have to be just opposite signs, but the same number. Everybody's okay there? All right. So let's figure out where we have to look for tangent. Tangent goes from negative pi over 2 to positive pi over 2. That was the same as sine, except for the boundary values, but that doesn't really matter for quadrant speak. So again, we're looking in quadrants 1 and 4. So we're going to be looking here. Oops. Okay. And what are we looking for? Where the x and y are the same number but opposite signs. If I look in quadrants 1 and 4, the only place that happens is here, where the x is positive root 2 over 2 and the y is negative root 2 over 2. You guys agree? So my answer should be 7 pi over 4. I'm now going to check to make sure that's in our range, if that's an acceptable output. Oh no. 1.75 pi, that's too big, isn't it? What are we going to do? Subtract 2 pi. Yep, I'm going to skip making the common denominator this time, if that's okay with you guys. I figure I should do it at least once. But if we do, that's really the same problem we just did before, right? We did this exact same one when we did sine inverse of negative root 2 over 2. All right. So let's look at, I didn't do something when I did tan inverse to start, right? I didn't bother to check to see if -1 was in the domain for tan inverse. Why didn't I bother to do that? What's the domain for tan inverse? It's all real numbers, so I don't really need to check the inputs for tan inverse because you can do tan inverse of anything. Is that okay? All right. I figure I should mention why I didn't do that. All right. So if we look at the next one, we need to figure out where x over y is equal to square root of 3. Well, I'm going to think about square root of 3 as a fraction. But I don't see anywhere on my unit circle in quadrants 1 and 4 where the x-coordinate is 1 and the y-coordinate's a square root of 3, right? Take a look. Do you see any place where that happens? I don't either. But what about this point here? The x-coordinate is 1 over 2, and the y-coordinate is square root of 3 over 2. If I had taken this and I multiply it by 1/2 over 1/2, I need to be looking for the place where x is positive 1/2 and the y is positive root 3 over 2. That is specifically pi over 3. And since that's between negative pi over 2 and positive pi over 2, I know that answer's okay. How are we doing so far? Kate. Sure. Okay. Let's look at another similar but still related kind of problem. So let's say we were asked to solve the equation sine theta equals 1/2 on the interval from pi to 2 pi. Before we do this algebraically, let's look at what this problem is really saying graphically to give us some intuition. Please stop talking. Okay, so if I have the equation sine x or sine theta equals 1/2, let's say we want to graph y equals sine x, and we graph y equals 1/2. The solution is going to be every place where there's an intersection. How many intersections do you see? I see 5 on the screen, right? How many are there really? Infinitely many, because obviously the sine curve, each of these keep going, so you're going to cross infinitely many times. Well, that doesn't help us. But if we only want the answer that's between 1 pi and 2 pi, oh my goodness, Mr. Kulik. I goobered that one up pretty good, huh? Let's just do that. Yeep. If we're looking from pi over 2 to 3 pi over 2, I see exactly one intersection happening there, right? Okay. So what we're going to do this kind of a problem, we're going to start by looking at my interval. So on the unit circle, I'm going to find pi over 2 happening right there. Angles are getting bigger, so I'm going counterclockwise, and I'm going to keep going until I get to 3 pi over 2, which is right here. So we're going to be looking for an answer in what quadrants? 2 and 3, right? So where am I going to look? I'm going to look, because it's sine, I'm going to be looking at y coordinates equal to 1/2. So the only place in quadrant 2 or 3 where the y coordinate is 1/2 is 5 pi over 6. Is 5 pi over 6 in between 1/2 a pi and 1.5 pi? Definitely, right? 5/6 is bigger than 1/2, but it's less than 1.5. Everybody feel okay? All right. What if we will have cosine inverse? Oh, I'm sorry. Cosine of theta equals negative root 2 over 2 on the interval from 3 pi to 4 pi. So again, first thing I'm going to do is figure out what quadrants do I need to look in. So if I go and look at my unit circle, 3 pi is not on there, right? But I know that I can just keep going around and around and around on this guy, right? So if I start at 0, there's 1/2, there's 1 pi, 1.5, back to 2 pi, 2.5. So 3 pi starts here. So we go to 3.5 all the way to 4. Everybody okay with how I counted around to do that? What quadrants am I covering there? 3 and 4, right? Again, the quadrants are named just counterclockwise. What coordinate should I be looking at? What coordinate? X, y, because it's cosine. And what value of x am I looking for? Negative root 2 over 2. So I'm looking in quadrant 3 and 4 for the place where the x coordinate is negative root 2 over 2. There's only one place where that happens, at 5 pi over 4. Now if I check, is 5 pi over 4 in between 3 pi and 4 pi? 1.25, not between 3 and 4, right? Oh no, what should I do? Add 2 pi because it's too small, needs to get bigger. To add those two things, I'll make a common denominator. I'm going to skip doing that. Is that okay with everybody? Showing the work for the common denominator? We're good? That gets me 13 pi over 4, or 3.25 pi. That's in between 3 pi and 4 pi. So that answer is good. Everybody feeling all right so far, so good? Yes. Sure. Okay. Let's say we have tan theta equals root 3 over 3 from negative 5 pi over 2 to negative 3 pi over 2. What do we start by doing? We want to figure out what quadrants do we need to be looking at, right? Now I know that there's no negative angles on my unit circle, but that's okay. I'm just going to start at 0, and because we're talking about negative angles, which way am I counting? Clockwise, right? So 0, negative a half, negative 1, negative 1 and a half, negative 2, and then negative 2 and a half. So we're covering quadrants 1 and 4. Everybody's okay there? Now the tangents are tricky, right? Because tangent isn't just x or y, it's y over x, right? So I have to kind of look at both. So, okay, well, if it's just y over x, then I'm just looking for the place where the x coordinate is 3 and the y coordinate is square root 3, right? Do you see any of those spots on the unit circle? Where the x is 3 and the y is square root 3? I don't. Okay, what's going on then, Mr. Kulik? Did you give us a bum problem? I did not. There is. So this is the trick, is I'm going to think about 3 as the square root of 3 squared. Right? Those are still the same number, 3 and the square root of 3 squared. Why would I do that? What can I do with this fraction now? I can reduce it, right? And now if I look, now I don't see a place where the x coordinate is square root 3 and the y coordinate is 1. But I do see a place where the x coordinate is square root 3 over 2 and the y coordinate is 1 over 2. And that's the location that I'm going to want. So looking in quadrants 1 and 4, where the x is the square root 3 over 2 and the y is 1/2. We have that. Everybody agree? Got to be careful on that, though, because it's easy to get your x's and y's flipped around, right? So theta equals pi over 6. Is that between negative 2.5 pi and negative 1.5 pi? No, it's too big, right? So what should we do? Subtract 2 pi. When we make a common denominator, oops, that's not what I want. I get negative 11 pi over 6. That's the same thing as negative 1 5/6. Is that between negative 2.5 and negative 1.5? If you're not sure, think about it like on the number line, right? You know, and 5/6 is what, like 0.8 something or another? So yeah, that one works. Should be good. We're going to do one more example, then we're done for today. Sound good? Okay. Whoa, hold on, Mr. Kulik. Hold on a second. We haven't done anything with cosecants in it yet. Whoa. Hold up. That's not fair. Okay. But what is cosecant the same as? It's the reciprocal of sine is correct. So I have the equation 1 over sine theta equals 2 over 1. If I flip both sides of this equation, that's just the same as doing sine theta equals a half, right? That we can do. So if you run into a secant, cosecant, cotangent, all you're going to do is flip it so that it's a sine, cosine, or tangent problem. Everybody's okay with that plan? Cool. All right, let's figure out where on the unit circle 11 pi over 2 to 13 pi over 2 is. Holy shnikes. All right, let's start counting. 0, a half, 1.5, 2 and, or I'm sorry, 1, 1.5, 2, 5 over 2, 6 over 2, 7 over 2, 8 over 2, 9 over 2, 10 over 2, 11 over 2, 12 over 2, 13 over 2. Everybody's good with how we counted that out? So we're going from, or we're looking in quadrants 1 and 4. So in quadrants 1 and 4, if we look for where the y coordinate, because we have sine, is 1/2, that's right there. So our answer should be pi over 6, right? Is pi over 6 between 5.5 pi's and 6.5 pi's? Well, no, Mr. Kulik. What am I going to have to do then? Add 2 pi, and we're going to have to do it more than once. You are correct. So that's 13 pi over 6. That's 2 2/6. Still not enough, right? Or 2 1/6, I should say. Right, because this is 5.5, and this is 6.5. So let's do it again. So that's 4 1/6. Still not enough. Oh my goodness, Mr. Kulik, this is just cruel and unusual punishment. It's fine. You're just adding 12 to the numerator. Everybody okay? That's kind of as hard as it'll get. That's not bad, right? Now, what we've done today is foundational to everything we're going to be going forward doing in this chapter. Like if you can't use your unit circle and figure out the quadrants you need to be looking in, life's going to get tough real quick. This is a really good foundational skill. We're stopping here because this is how important I feel like this skill is. I don't want to move forward until I feel like we've had some practice and we have this. What I'd like for you to work on is this worksheet 1. Worksheet 1 is just like exactly these problems we've just been doing examples of, right? Like these last 4 examples or whatever, just like the ones we're doing here. Everybody okay? When would this be due?
Next Sunday.
Not this Sunday, but next Sunday. What's due this Sunday? Nothing. Yeah, we did everything. You turned in everything from chapter 3 last Sunday. Okay? Now, please do this assignment before next time we meet. It'll make a world of difference if you've practiced these skills before we meet again. Okay? Use your unit circle. Have it out next to you when you're looking at this. There's not much work to show, right? You're just looking at the unit circle. Everybody's okay? We have, 20 minutes left or 25 minutes left of class, something like that. Get your stuff out. Do a couple while it's fresh in your head. Do a couple, right? Get started on this. Ideally, there's 12 problems. If you can do one problem per 2 minutes, which seems pretty realistic, you could finish this today. Even if you can't do 2 minutes per problem, you probably come darn close to finishing it today and have 10 minutes left of something to do later on, which again, pretty good deal, right? Get your stuff out. Do something. Any of it. Part of it. Some of it. Anything. Please.